starting. Our first presenter is Dr. Marco Quadrelli for welcome and the introduction.
Thank you, Farbod. Welcome everybody to the fourth quantum engineering workshop, which is sponsored by Caltech, CAST, ASME, and Cal Poly Pomona. Okay, so I'm going to open this by giving you the vision. We have a vision here, and the vision is that we are trying to integrate emerging quantum technologies with existing or developing engineering systems to enable novel space and terrestrial science opportunities. So, and I'll give you some motivation later. So we're trying to bring together a community and engineering physics experts to promote the intersection, because in our experience, there's a very established quantum physics community and a quantum technology community made by engineers, and the language that is not there yet, the language to communicate. So we're trying to develop that language. And so that means developing a community of practice. Hopefully this is the fourth workshop, but there will be many more ahead of us. Initiate research collaborations, and also change the curriculum. I'm not a professor, but I work with Farbod and other my collaborators in academia to see where we can make the change. And there are many people, you know, I'm always, when you put names of people, you always leave somebody out. So I just put some here. There's many people at JPL. I'm from JPL. And many people from outside JPL that have supported this effort in the last years. So let me tell you, because I'm from JPL, let me tell you a little bit about JPL. JPL is a federally funded research and development center. Is halfway between a Caltech laboratory and a NASA center. And we have over 20 spacecraft and 12 instruments across the solar system right now. So and we're always trying to push the boundary. And JPL, so I mean, you can go online and look at this, but the reason for that preface is to give you a little bit of context here. So, and this is my view, okay, my personal subjective view, but we've shown this multiple times and people have not complained too much. So if you kind of divide space, so universe slide, okay, into classical systems, quantum systems in the quantum regime or classical regime, the slide that I showed you before is basically residing up there, okay, in a general sense. Now, please bear with me. You're not going to see numbers in this presentation. I'm trying to give motivation and vision. So this is a top-down description of what we are discussing here. There is also a pretty established community of people that fly things like LISA, gravitational gradiometers, GRACE, and so on, with the intent of developing, measuring, doing gravitational measurements, for example. There's another very strong community that works on cold atom interferometry, quantum gravity gradiometry, Bose-Einstein condensates, et cetera, quantum computing. And there's another community that is emerging that Farbod and I and others have started, which is which is a hybrid where we have existing engineering systems, and both Farbod and I, we work on mechatronics, work on robotics. So there are robotic platforms where we now interface those platforms with quantum cryptography experiments, quantum entanglement experiments, doing photon counts, and things like that. So this is an emergent area that we hope to develop even more in the course of this discussion. So let me go to, okay. So what is quantum engineering? That's the title of the workshop. What is a very highly interdisciplinary field where we talk about, yes, engineering, classical engineering, but also aspects of engineering that have no classical analog. And those of you, and many of you that work on quantum technologies know superposition, interference, entanglement, and very broadly, there are three areas. One is quantum computing and simulations, where, I put a picture there of a quantum computer, which is a pretty big thing. And we don't have a quantum computer flying anywhere yet because it's heavy, it needs to be cooled down to very low temperatures. So that's one area. Another area is quantum communication, where we have done experiments, not me, I mean, others have done experiments of combining classical channels with quantum channels over very long distances pretty successfully. And then there's the area of quantum sensing and metrology, where, as I said before, there's all these things like atomic optical clocks, Rydberg sensors, magnetometry called atom interferometry, and they have different levels of maturity, and I'm going to get into that. So there are three regimes of applicability that we are trying to cover here. One is when you try to act classically on classical systems, and the majority of work that has been done where I come from at JPL historically has been on that. It's been robotic systems or aircraft, spacecraft that behave classically. There's another regime of applicability, which is what I just mentioned before, where now the quantum principles start to become very meaningful. In fact, it's the reason you do the measurement. So now you act quantum mechanically on quantum systems. And again, this new area is where you're doing the hybrid. So act quantum mechanically on classical systems. So in my view, and we have published in this area a little bit, this is still very new. And there's a big space to explore with these characteristics. So again, quantum engineering is an ecosystem that covers multiple disciplines. You can see the circular ones around there. Those are the classical science and engineering disciplines. And the text in between is where things are developing now. And the beauty of this workshop is that by bringing engineering and physics experts together, we hope to even populate this ecosystem even more. And in fact, in the last three workshops, we have already covered this ecosystem quite extensively. You can look at the recordings of the past workshops, and you realize that. And same thing today. We have a long list of illustrious speakers. I'm going to learn a lot today. So I would venture to say that okay, we need to give some structure here, because when we design, for example, a space mission to go to study the solar system, there's someone in the science community that gives the push and says, okay, we really want to go and do this measurement. So how do we do this measurement? There's then a mission objective that is enabled by a capability. Capability could be, well, okay, you need a propulsion to get there. We need a quantum computer to do something. And that needs to be implemented by some technology. That is the pool. The technology pools now. And so what we are talking about in this workshop is that quantum engineering is up there, which I just call it a game-changing capability. And in the literature, people have talked about the first quantum revolution, the second quantum revolution. I would venture to say that we are beginning, if we are successful, merging these two communities to spearheading the third quantum revolution. So I have to say, because I talk about science pool, this is what the national academies publish, and there's many more reports like this on different areas, like earth science, quantum computing, astrophysics, heliophysics, planetary science, biological, physical sciences. And it turns out that in recent times, actually the last planetary science decadal survey had more than ever their request to look at quantum computing, quantum sensing, that hadn't been done before. So now we have a need from science. We have the pool. And so now we need to fill that from the technology side. This is what this workshop is about. And in the other areas, astrophysics, same thing. And I highlighted in yellow the mentioning in those reports of quantum engineering related topics. Earth science, there's a quantum gravity gradiometer. In fundamental physics, there's quantum precision measurements and And a more recent report, 2019, indicates that there is no fundamental reason why we wouldn't be able to build a effective quantum computing that can achieve quantum supremacy, but also practicality, which are different things to keep in mind, okay? So I will say, because I'm JPL is also NASA Center, we are used to talk about technology readiness level. Technology readiness level is the level of maturity. Technology readiness level of 1 is where you have an idea, get up in the morning, say, oh, I want to go to Alpha Centauri, okay? Technology readiness level 9 is when you are flying, okay? You have built, you are flying. I have found with great interest that there is a quantum technology readiness level, which goes in parallel. And there's an example there for quantum computing with a citation. And in terms of quantum technology readiness level, which indicates the level of maturity over time, I would say now that I'm framing those 3 areas that I discussed at the very beginning with their level of QTRL, of maturity. This is my view, okay? I've done an extensive digging into the literature, talked to a lot of people. This is my conclusion. But bottom line, the most mature of the 3 areas is the quantum sensing area, which is the most heavily funded too. The other ones are also getting there, but not quite. There's such a thing as this hype cycle, and I have to collocate things in the proper perspective, and that's what I'm trying to do here. I hope some of you agree. So now at JPL, I've done for many years guidance, navigation, and control. That's what you do when you try to point the spacecraft or navigate the spacecraft. And so I look at things in quantum engineering with that perspective. That's my professional bias, I guess. And so guidance means when you are determining the path of the vehicle, navigation, and when you are trying to determine where the vehicle is, and control is how you correct and keep the vehicle on track, very generically speaking. So, and this is what you do. This is what you do. You measure, you take measurements with your sensors, you do some decision, you plan, you control, and then you keep monitoring and observing. So quantum engineering, the areas, those 3 areas that I presented to you a moment ago that we are covering in this workshop today, they kind of place themselves up there. And I would say that, of course, like every area of science and engineering, there are things that are more mature and less mature. So, for example, one thing that is totally lacking in quantum engineering, and I think I had something else there, but it's not showing up. It doesn't matter. The bottom line, for example, the system engineering process, or the system integration, that is what enables full space missions like the ones that I showed you at the very beginning of JPL does, is inexistent. There are no processes yet in place to accomplish that. That is a big gap, because if you don't have that, then you cannot put people together. We cannot develop system requirements. You cannot test. You cannot do verification, etc. So, for example, but there are other areas that you can see there. So to do this, of course, you need one-of-a-kind people, because I'm an engineer. I didn't study quantum mechanics in school because I'm a mechanical engineer, but I studied it afterwards with great pain, and I continue studying. I'm a student. And I'm very fortunate to work with Farbod and others to do this that we're doing today. I'm learning a lot. I'm starting to speak the language, okay? And so Farbod is a professor. He has already experimented and tested very successfully in his curriculum with his class, how to train the new young folk, the new students, to be prepared to speak the quantum engineering language. So, and not only at Cal Poly, other universities across the country, they are doing this very successfully. So I invite those of you, because we're at Caltech, most of you are academics, you're professors, please follow along the same lines. And we have already, I mentioned our publications, and we can send them out if needed. I would like to pass the ball to Farbod now to do the other part of the presentation and introduce the workshop.
Thank you very much, Dr. Quadrelli, for this great introduction. So, as Dr. Quadrelli mentioned, we are here really to learn. So we are trying to learn what is quantum, and that's why we have the experts here. Dr. Clauser, John Clauser is here. So we're learning from him and others who are experts and try to see how we can apply these kind of technologies to our fields. Okay. And so we have these workshops, so we can basically have this community. And also, so this is one of the first workshops. We had many experts, and first and second, and the third workshops again. We had many, and this is the 2024, and we are hoping to continue again. We would like to learn more about quantum, and then how we can apply that to engineering. Today, we have the introduction. I have some more few slides just to finish this introduction, and then we will continue. Dr. Clauser will give us the keynote speech on experimental proof that non-local quantum entanglement is real. And then Siparis Michalikis from Caltech talk about quantum advantage. And then we have Professor Mark Wallace, who will be on Zoom presenting. And then we will have a break, a lunch break. And then after the break, 1:30, we have Dr. Jens from TOE Labs, 2 o'clock. He will be on Zoom, not in person. And the location is different. It's not here, is in the aerospace labs. And then we have at 2 o'clock, Dr. Reinhardt, and then continues with Dr. Paolo from MIT, Dr. Ander from Harvard, Jason Hyun from JPL, who will talk about the new JPL Space Quantum Innovation Center. And just for your information, there is also a new quantum center at Caltech, which is now under construction and will be completed in 2 years. So this will be a good opportunity to find out what can be done to have joint collaboration between Caltech and JPL. Then we have Professor Mansour Shaiban from Princeton and Andrew Philip Conrad from the University of Illinois Urbana-Champaign. He will talk about vehicle-to-vehicle quantum key distribution, which is, I think, one of the most kind of relevant to what we do or what we're trying to do. So bringing quantum again to engineering, like vehicles, systems, or engineering systems in general. And so he is doing amazing work, and we will present his work. He's a student of Paul Koyat. And
okay, so I just would like to continue briefly the introduction with a few minutes left. So we are aware of I think I'm sharing the correct slide. So we are aware of the national quantum initiatives that is now trying to promote application of quantum. So what we are trying to do, because I like to compare what we are trying to do with biomedical engineering, because it might be clearer of the purpose. So in biomedical engineering, there are many fields, many aspects. So, but you can say, I want to work in robotic surgery. Okay, so that's specific. So what we are specifically trying to do in quantum engineering, obviously quantum engineering, like biomedical engineering, is a very big area. But we are trying to see how we can, as an engineer, as a mechanical engineer myself, or electromechanical engineer, and Dr. Quadrelli and our colleagues, all collaborators, we are trying to see if you have a mechanical system and combine it with the computer technologies, early computer, then we have the state of the art, which you know, you are aware of it, self-driving cars, robots, and so on. But then the question is, now if you have the state of the art and combine that with quantum technologies, then what would be the result? So this is more like an open question. See what can we do, or what is the mechatronics of such systems? So first we need to know, how do you really combine this? How do you take advantage of, for example, quantum communication between two robots for multi-agent cooperative robotic applications. So these are the questions we try to answer. And we are here really to learn from you rather than, and we are only promoting this. So we created this quantum robotics page on Wikipedia. So we just coined the term quantum robotics, and we would like you to help us to basically create or establish this area. So that's the purpose, and hopefully you get your help. And please feel free to edit this page on Wikipedia and add your knowledge and contributions to this field for us so we can learn from you. So the idea again to use quantum technologies in our case is robotics, but of course everyone has different expertise. We have a lot of amazing work is going on in algorithms, materials, detectors. So we are not really doing that specifically. We are more interested in quantum robotics. So yeah, we are trying to find out what can be done in that area in terms of the quantum robotic. And for example, how can we use quantum teleportation in control of dynamic systems? So that's it, maybe more like a question than answer. So we are trying to come up with some kind of concepts for that. Recently we also, for example, we try to, everything that we do in classical system, we try to see what is the equivalent quantum version of that. So how can we combine quantum entanglement with brain-computer interface, PCI, and I mean, this is just a combination of technologies. It's not a new technology. We're just combining technologies, but again, this is like starting of this field. So we would like to ask you to help us to understand how we can continue. We have learned from the experts and learned how to do quantum entanglement. Specifically, we are interested in experimental because the theoretical work is already done by experts, and we are there is a lot of good work already going on, but we are trying to focus on the experimental side and learning from the physicists to how to do that. And we are doing it right now in the lab. We did the Bell inequality with the help of my colleagues who are again physicists. I'm not a physicist, I'm an engineer. So especially Dr. Galvez helped me to do the experiment in my lab. And again, we are trying to learn from experts. That's why we have Professor Dr. John Clauser here to help us to understand better. And then we're trying also, in terms of education, we try to bring more quantum to undergraduate education in mechanical engineering, aerospace engineering, as well as electromechanical and related fields. We know that electrical, usually they have some courses, or computer, they have some courses already, but we are really missing this in mechanical engineer fields and related like aerospace and so on. So we try to see how we can bring this, and we did that in the classroom. We tried to teach. So I've experienced that in undergraduate education with teaching quantum entanglement, experimental quantum entanglement in the class, and actually some of the students are here, and they took this course with me. Eric is here. He took the course, and so I gave them few lectures in the mechatronics, only few lectures talking about experimental quantum entanglement. And they understood it. They didn't need any theory, or it was complex theoretical kind of approach. They just need to see the experiment and learn about each component of the experiment and really do the experiment. So understanding quantum entanglement experimentally is not that complicated. So we can learn. I learned it myself. I didn't take any quantum mechanics course. I'm not expert in any theory or quantum computing. I don't need to be, and I don't really, because there are already so many people experts in those fields, and really we are as mechanical engineers trying to contribute to our field. So we can do also remote experiments. We did that. And we published that experiment, or even we can do double slit single photon experiment. So I would like to stop here. We have 2 minutes, and then I'll introduce Dr. Clauser, John Clauser, after that. So if there is a question, maybe about 1 minute time, please let us know, maybe 1, 2 questions. And Dr. Quadrelli is here if you have any question. And there's a microphone if you like to talk, or if you are in there's a Q&A, and there are actually questions in the, okay. Can you hear us in the, okay. So by the way, we have 950 or more than 950 registered participants today. We are using 2 Zoom links, but I think at each time we have about maybe 200 participants, as you see here, not more than that. But the total registered is about 1,000, I would say, easily to say. So, yeah. If there's no any question, I'll start with the introduction for the next, for the keynote. Yes, go ahead.
Hello. Yeah, so I have a question for Dr. Quadrelli.
Okay.
So what are some applications of quantum engineering at JPL specifically? Is it mostly quantum sensing or?
Well, as I said, there's a significant, a very large number of people for many years working on quantum sensing and developing detectors, developing systems to do measurements in different areas, like fundamental physics measurements or emerging areas like radar. But the maturity is still not high. So, it's research and development. Some of the things that we are trying to do is what Farbod just showed with integrating technologies that are already mature with quantum protocols or photon counting techniques and entanglement based in an attempt to develop new ways to do measurements. So,
Thank you.
Thank you.